Welcome to the Nuclear Weapons 101 series, a compilation of short presentations on nuclear weapons-related topics. The goal of this series is to improve nuclear literacy across the Department of Defense and promote a greater awareness of the critical role nuclear weapons serve in maintaining the security of America and her allies. These presentations are produced by the Nuclear Science and Engineering Research Center and Office of the Defense Threat Reduction Agency located at West Point, New York. This presentation is entitled Why Nuclear Weapons, and it serves as an introduction to the Nuclear Weapons 101 series. The purpose of this briefing is to describe the principal differences between nuclear and chemical explosions. A familiarity with these fundamentals, as well as with the associated terms and units of measure, will better prepare viewers for future presentations on more technical topics, such as the prompt and residual effects associated with nuclear weapons detonations. First and foremost, the term explosion refers to a sudden release of stored energy, which typically precipitates some measure of destruction. Therefore, to effectively contrast nuclear and chemical explosions, we will analyze them both in terms of explosion yield, burn time, and temperature. Let's start by considering chemical explosions. Chemical explosions occur when energy is emitted from chemical reactions over very short time spans. The reactions produce hot gases that expand rapidly and give off large amounts of heat. In fact, the gases are formed so quickly they compress the surrounding atmosphere, driving up the local pressure within a fraction of a second, which produces a shock wave and shock heating of the air that propagates outwardly in all directions. So, of course, chemical explosions can create tremendous destruction depending on the amount of explosive fuel. In terms of our comparison criteria, if we consider only 1 kilogram, approximately 2.2 pounds, of trinitrotoluene, or TNT, the energy yield is around 4.2 million joules. Considering it only takes around 400 joules to break a human bone, that's a significant amount of energy released from just 1 kilogram of material. Additionally, in terms of the chemical reaction time span, 1 kilogram of TNT typically burns in about 10 microseconds, which is very fast. Part of the reason why chemical explosions are so destructive is they release all that energy in such a short time span. Lastly, typical temperatures for the hot gases created from a chemical explosion reach around 5,000 degrees Kelvin. If you consider the human body as only 310 Kelvin and the melting point of steel is around 1800 Kelvin, it's clear that chemical explosions get extremely hot, hot enough to instantaneously change a solid to a gas. Now, if we compare the values for chemical explosion yield, burn time, and temperature to the equivalent values for a nuclear explosion, we begin to understand some of the key differences. For this example, let's assume our fuel consists of only 1 kilogram of uranium-235, so the same total mass as the TNT we discussed earlier. First off, in the case of the nuclear fuel, the energy is not emitted from chemical reactions. Rather, the energy release is due to an instantaneous cascade or chain reaction of uranium atom fissions, which, in total, releases a tremendous amount of energy because the matter is made up of a lot of atoms. In a practical sense, the energy released from our 1 kilogram of nuclear fuel is around 4.2 times 10 to the 13th joules, or around 10 million times greater than the energy released from our TNT. Additionally, the entire fission chain reaction takes significantly less time than the chemical reactions in TNT. Fundamentally, this means the atoms are splitting at rates and over timescales well below those found in chemical reactions. In fact, our entire 1 kilogram of uranium-235 fuel would burn in about 0.1 microseconds. This means, hypothetically, we could detonate 100 1 kilogram nuclear explosions, one after the other in a series, in the same amount of time it takes for 1 kilogram of TNT to detonate. Lastly, let's compare explosion temperatures. Unlike our chemical explosion, which reaches around 5,000 degrees Kelvin, our nuclear fuel has the potential to burn as hot as 50 million degrees Kelvin, or around 10,000 times hotter. These are temperatures higher than those found on the surface of the sun. At such temperatures, even the heavy metal nuclear fuel is heated beyond a gas and into a plasma state, which results in a tremendous amount of electromagnetic radiation, in addition to the neutron and gamma ray radiation produced from all the nuclear fissions. Chemical explosives simply cannot reach anywhere near these temperatures, so they have no associated electromagnetic radiation. Therefore, when comparing a chemical explosion to a nuclear explosion, one may reasonably argue the only similarity between the two is the word explosion. Finally, to return to the title of this presentation, why nuclear weapons? Well, in the words of the Manhattan Project scientist Dr. Robert Server, the objective was to produce a practical military weapon in the form of a bomb, one that utilized a fast neutron fission chain reaction. The success of the Manhattan Project in 1944 proved not only that nuclear weapons were feasible, it also demonstrated their practical utility as military weapons. Since a single nuclear device may replicate the devastation of thousands, if not millions of tons of TNT, this is exactly why the Department of Defense typically measures nuclear explosions in terms of kilotons. 1 kiloton of nuclear yield is roughly equal to the explosive energy released by 2.2 million pounds of TNT. This concludes the presentation. If you would like to continue learning more about nuclear weapons and their effects, please click on the link below. Thank you for your attention.